Hello, I am Dr. Ekaterini Klepousniotou and I'm a lecturer at the Institute of Psychological Sciences at the University of Leeds. Today I will be talking about magnetic resonance imaging, or MRI, and functional magnetic resonance imaging, or fMRI. So magnetic resonance imaging, or MRI, uses a very powerful magnetic field to reconstruct an image of the body. What I will be focusing on will be the brain, because that is my interest and my area of expertise. We've been studying the living brain since about the 1950s with Dr. Wilder Penfield, the founder of the Montreal Neurological Institute in Canada, being the pioneer in this area of research, when during surgery for the removal of epileptic foci in patients, he would stimulate the brain slightly with electrodes, and he would record what these stimulated areas of the brain would do, what was the function of those areas. Now, this type of surgery for the removal of epileptic foci, happens under local anesthesia because the neurosurgeon wants to know exactly what is going on during the procedure, and he wants the patient to be awake so the patient can respond to stimulation. And remember, the brain doesn't feel any pain, so local anesthesia works fine for that type of surgery. Since then, though, we've come a long way in being able to study the living brain and understand how the brain works. Crucial in building MRI scanners has been the discovery of nuclear magnetic resonance in 1947 by Felix Bloch and Edward Purcell. They simultaneously discovered nuclear magnetic resonance, and that discovery led to a Nobel Prize in physics in 1952. Paul Lauterbur introduced concepts necessary for making images in the 1970s, and then Raymond Damadian constructed the first full-body MRI scanner in 1977. So nowadays we have different ways of looking inside the brain. We have the traditional way, which is anatomy, or we have more current imaging techniques like the MRI scanners. So what is nuclear magnetic resonance? How can we make a magnetic resonance image? And how can we use MRI to study the brain? Let's try and address these questions. So I'm going to talk a little bit about nuclear spin. So certain nuclei, like hydrogen, sodium, and phosphorus, have a spin. So they act like sub-microscopic magnets. Atoms and nuclei move around freely, and the spins usually have very random orientation. However, if we put them in a magnetic field, the nuclei are aligned, and they spin like tops. Nuclei can actually listen and talk to each other through radio frequency waves. So what does this have to do with brains, one would ask? Well, think about it. The body is made up mostly of water, and water is made up of hydrogen and oxygen, of course. But it is hydrogen that is important to us, because if you remember, hydrogen has a spin. And it is these nuclei that we can actually capture in the images. So we get the raw image, and through a Fourier transformation, we actually have a reconstructed image of the body. In our case, we care about the brain. So a reconstructed image of the brain. So how strong is the magnetic field of an MRI scanner? Well, a simple comparison. The Earth's magnetic field is equal to 0.00005 Tesla. Tesla is the unit of measurement. And what about an MRI scanner? Well, if you hear that an MRI scanner is 1.5 T, that means 1.5 Tesla. So many times stronger magnetic field than the Earth's magnetic field. Currently, most MRI scanners tend to be 3 Tesla, but there are also MRI scanners that are 4 or 7 Tesla. So MRI enables us to look inside the living brain. We can study the development of the brain, so we can actually have scans of babies, embryos even, before they are born, at the time they are born, and then study development throughout and see how the living brain actually develops. We can also use these scans to study pathology or sickness. So we can study if the brain actually shrinks as we get older, for example. There are different types of scans we can acquire. So if we talk about just an MRI scan, that means that it is a structural scan, which means that we actually see the anatomy of that organ of our body. So talking about the brain, we see the anatomy of the brain. We can also talk about diffusion MRI, which shows actually the direction of the nerve cells. That is, the connections between the areas that do all the processing. We also have MR angiography, which shows us the blood vessels of the brain. And finally, we can have what we know as functional MRI or fMRI, which actually shows us brain activity. So fMRI is a type of specialized MRI scan used to measure the hemodynamic response, that is the change in the blood flow related to neural activity in the brain of humans or other animals. The assumption is that when an area of the brain works to process some material, to do some kind of cognitive processing, then that area needs more oxygen. And oxygen is carried by the blood. Now, when oxygen enters that area, it is consumed, and then the blood that leaves that area has less oxygen in it. And this is exactly what we can capture, that difference between how much oxygen came into an area and how much less oxygen the blood had leaving that area. That's what fMRI can capture. So we measure the BOLD response, or the blood oxygenation level dependency, that is the change of the local ratio of oxyhemoglobin to deoxyhemoglobin. Now, the brain consists of many different cytoarchitectonic regions that were described more than a century ago, actually. The most commonly used map of the cytoarchitectonic areas of the brain is the one by Brodmann that was published in 1909. The assumption is that different areas subserve different functions. So in other words, to make it a bit simpler as a concept, think of it as a map. Think of the brain as a map of the world. We know where the borders lie, so we know, let's say, where France is compared to Spain and Poland, and that's the cytoarchitecture. What we are trying to understand is what each one of these areas do. So what is France famous for? Let's say we've discovered that France is famous for wine. Then we want to know what Spain is famous for, and so on and so forth. So what we are trying to do with functional MRI is to understand the functionality, the contribution to cognitive functioning of these specific areas in the brain. So fMRI is our newest method in understanding how our brain works. In the past, we had to rely to anatomy or brain stimulation. Nowadays, we can also study the healthy living brain with functional magnetic resonance imaging. So how does that work exactly? So you have to build a cognitive task to study the cognitive function that you're interested in, and at the same time you acquire functional scans of the brains of your participants. So you actually test your participants inside an MRI scanner. So for example, my area of interest is language, so again I'm going to talk about language. Let's say we want to find out which areas of the brain are differentially activated when we generate words. So we have our participant lying in the scanner and we ask the participant to silently generate as many words as they can think of, starting, for example, with the letter T. At the same time, we are scanning the brain, the activity of the brain of our participant. We have to test a number of participants, of course, and then put together all their results to analyze and have an effect, a group effect. And this way, we can see which area of the brain is differentially activated when we ask people to generate words. Now, in order to actually capture an image and see what is happening, you have to have a contrast. fMRI results always come as the result of a contrast, so we would have to have a control task where we would ask our participant just to, for example, simply close their eyes for 1 minute and try to think of nothing, which is a very hard thing to do, but that, for example, could be our control task. So then we would take the images that were generated when the participant was silently generating words and subtract the images where the participant kept their eyes closed and see the result. So the areas that would remain, that would still be activated after that subtraction, would reflect the effort of the participant to generate words. So you can think of this way, and this is a very simplified example of how we would design a task for an fMRI study, but you can think about it and you can design tasks to study memory functions or attention or spatial orientation or any cognitive function really, because we know all cognition is generated in the brain. So let me quickly summarize what we've discussed about functional magnetic resonance imaging. It has a very high spatial resolution, so it can give us with accuracy which areas of the brain participate in particular type of cognitive processing. It's not very good at temporal resolution, so it cannot tell us millisecond by millisecond what is happening in the brain. It's like taking static images of the brain rather than a fast video of it. It's sensitive to what sorts of cognitive processes are active, and it is good for mapping the brain and helping us understand what areas do what. And I think this is where I'll finish for today with the description of magnetic resonance imaging and functional magnetic resonance imaging. Thank you for listening.